All right, hello again, pre-capitalist people. So today we're going to continue on with talking about exponential and logarithmic functions. If you remember in the last couple of videos, we talked about how to solve exponential functions and how to solve logarithmic functions. Today is going to be all about solving exponential functions, but not only solving them and kind of getting that exact answer that we talked about previously, but we're going to use a calculator today to actually get actual answers for real life kind of situations of population growth and stuff like that. The good news is all of these functions that we're going to see can all be modeled with this function right here. Now, a couple of things about that notation. The big one that people kind of get thrown off is this a sub 0. It's just the initial amount. So whatever amount you start off with, that is going to be your a sub 0. During the video or in class, if you hear me say the term a naught, that's kind of an old school way to say a 0, but it's still just the initial term. And then you see that k term, so e is our number e. The k is our rate of growth. Now, it's not as easy as calling it a percentage, but it's going to be some kind of decimal. But notice it can be positive or negative. If it's a positive number, it's going to be a growth function. So the amount, like population or whatever, is going to be increasing. If k ends up being negative, you know it's going to be a decay function. So your amount that you have, whether it's population or whatever, is always going to be decreasing through time. And we do use the variable t in these functions because they're always in terms of a future amount you have in some kind of function of time. Okay, so I've got 3 examples that I'm going to try to run through. I'm going to try to not make this video too long. The one thing I will say is I'm not going to switch screens going back and forth between my calculator and the answer. I've got the answers kind of written down on a piece of paper. I'm going to show you how I get them, but I just don't want to take the time to go back and forth. If you have a calculator that you're using, you know, a TI, an 84, or Inspire, or Desmos, if you need help using that, please let me know or let your teacher know, and we can do that. But the main thing is I want to see how the functions work. Okay, so here's the first kind of function, or first kind of problem. I'll let you read the problem. If you need to pause the video real quick, you do that. But notice in this case, we're giving you the equation, including the k value, right? So the first question is, what is the initial size? Right? Remember that a sub 0, that number in front of the e, is your initial. So the initial size is 50, because it's that first number right here, right? And now is when the fun begins, though. So letter B, how many rabbits are there after 6 months? The one thing you got to make sure and do when you read the question is know what your time is talking about. So in this case, my unit of time is per month. So to do this, all I got to do is plug in 6. So I'm going to do 50 e to the 0.04583 times 6. And you can put that in the calculator. And if you do that, you end up getting 65. Now, to be clear, the calculator is not going to give you a clean answer. It's going to be 65 point something, 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 something. But use some common sense. We were talking about rabbits. You can't have half a rabbit. Okay, so you can either truncate, which means just kind of getting rid of the decimals, or you can round. I personally, when it comes to population, I personally just truncate and I just talk about the whole number. But if you wrote this number as 66 instead, because I think it comes out to be like 65.8 something. If you wrote it 66, that would be okay too. Okay. Now for part C, for 2 years, again, you have to be mindful of the months, right? So this is going to be 50e to our k. 2 years would be 24. And then if you type that into the calculator, you end up getting, again, it's not a clean number, but when you get rid of the decimal point, it ends up being 150 rabbits. those are what I call plug and chug questions. When you just plugging in the time value and letting the calculator do the work and kind of going from there. Letter D and E, however, are different kind of questions. So on these two, now we're dealing with, we want to know when something will happen. So in other words, when you see this, that means we're solving for a T value, okay? So let's take a look and see how this works. The good news is it's going to work the same way every single time. So if I want my population to be 10,000, I'm going to set 10,000 equal to my function. So it's going to look like this. And I want to solve that for T. Well, we did that 2 videos ago when we talked about solving exponential functions, right? So the first thing we have to do, we have to isolate. So we divide both sides by 50. You can simplify this too. This ends up being 200, 10,000 divided by 50. You don't have to, but I'm going to just to make it a little easier to write. So this is going to be 200 equals E to all of that stuff. And then remember, we take the ln of both sides. When you take the ln of the right-hand side, the E and the ln cancel out, so we're left with this. And again, if you're not sure why that happened, go back and watch that previous video I did, and I'll link to it at the end of this video on solving exponentials. And then we got to divide by that decimal to get T by itself. So I'll write that over here. So T is equal to ln of 200 over 0.04583, which when you put that in the calculator, and remember, we're talking about time here, so this can be a decimal. This ends up being 115.608 months. If you want to know how long it is in years, you can just divide that by 12, and it ends up being 9.63. Now, is that really realistic? Can that size of land really hold 10,000 rabbits? Maybe not, but mathematically, that's when, and if it kind of continued on that same rate, that's how long it would take for there to be 10,000 rabbits. Letter E works exactly the same way. So if you wanted to quadruple, remember my initial population was 50. So if I wanted to quadruple, so 50, 100 is double, 150 is 3 times, quadruple is 4. So that means 200 equal to 50 e to the 0.04583 t. And again, isolate, so divide by 50. Already know that's going to be 4. Take the ln of both sides and then divide. So t in this case would be equal to ln 4 over 0.04583, which ends up being 30.249. That should be months, not moths. And then 2.521. Okay, so those honestly tend to be a little bit easier because you're given the K value. But again, so if you're given the time, it's kind of plug and chug. If you want to find the time, you do have to do this. You know, we have calculators at our disposal, and I'm sure you guys can probably come up with ways to not do the algebra, but we will not give you full credit unless the work is shown for the exact answer. And I want to be clear, this right here is the exact answer. Just like this right here is the exact answer. So we need to see that as well as the decimal approximation you're doing this. Okay? Let's go on to the next example where all of a sudden we don't know what K is. So if you see number 2, we have a culture of bacteria. We know it starts with 8,600, and after 1 hour, there's 10,000. That's all we know. So we have to take that format. Again, it's always going to be in that format of this, right? So we know A is 0. We know our initial, and we also know an A and a T, where if T is 1 hour, we know A is 10,000. So we can use that to find K and write our equation. So what's that going to look like? It'll be that. And now we do the exact same thing to solve, but in this case, we got to solve for K just to get that growth rate. So again, isolate, divide by 8,600. And I'm not even going to bother simplifying that because I'm let the calculator do the work for me. And this is e to the k. K times 1 is k. Take the natural log of both sides. So k is equal to the ln of that fraction. Now, if this was a college course, you would probably be expected, even on like the next few questions and in the equation, to use that specific value for k, not even worry about what the decimal approximation is. But since we're a high school course, I'm going to go ahead and do this on the calculator, and k in this case ends up being 0.1508. When you do this, folks, please go to at least 4 decimal places for the k value. At least 4, if not more. Okay? So now we have our equation. So now our actual equation is 8,600. Remember that the A naught, the initial value, never changes. So it's 8,600 e to the 0.1508 t. For B and C, those are our plug and chug ones. And remember, it is in hours, so letter B is just plugging in 2. And that ends up being 11627. Again, it's a decimal, but we can't have half bacteria, so I'm not worried about the decimal. And then for C, after 3 days, that's 72 hours. Which is a very large number, coming up to 446,574,805. And then for part D and E, again, those are solving questions. So how many hours will it take to double? So to do 8,600 times 2, that's 17,200. And again, same thing that we've been doing since Thursday, since a couple days ago. Divide by 8,600. We know that's going to be 2 because it's double that. So 2 equals e to the 0.1508t. And then you take the natural log of both sides and solve. So t is equal to ln2 over 0.1508, which is going to be equal to 4.596 hours. And again, that's okay to be a decimal because it's time unit, so it's good. Letter E is exactly the same way. 1 million equals 8,600 e to the 0.1508t. Divide by 8,600, take the ln. So this is going to end up being ln of 1 million over 8,600 all over 0.1508, and that's going to be 31.538 hours. And then I got one more question on here. I'm going to try to zip through. I'm hoping this video doesn't end up being too long, but I do want to do one more example with half-life, because that's a very common one you're going to get also. Notice this problem in example 3, all you're given is the half-life of 87.32 days. And then we start with a sample size of 1,000 grams. So we know that's our A sub 0. But again, we don't know K. But it is important we know what it means to be the half-life. Well, that means when this much time has passed, then there's going to be half of the amount of stuff we have left over. So to find K, we can say 500, half of the initial, half of 1,000, equals 1,000 E to the K times 87.32. Divide by 1,000 on both sides, so you got 1/2, 500 over 1,000. And then in this case, your K is going to be ln of 1/2, or 0.5, either way you want to write it, over 87.32. Now, just to note, your K in this case is going to be a negative because it is a decay value. Okay, when you put that in your calculator, you should get negative 0.0079. So my function is 1,000, again, initial doesn't change, negative 0.0079 t. So how much is there after 180 days or after a year? Again, my time is in days, so that's just a plug and chug. So 1,000 e to the negative 0.0079 times 180. And that ends up being 241.231 grams. And again, it's an amount, so decimals are okay. After 1 year, that's 365 days. I don't know a year anyway. We're going to act like it's not a leap year. And that ends up being 55.939. And then the last one, when will, so you're looking for time. So you set 100 equal to the function. Isolate, divide by 1,000. 100 divided by 1,000 is 1/10. Take the ln of both sides and solve. So t would be equal to ln of 1/10 divided by negative 0.0079. And that is approximately equal to 291.466 days. And that is how you solve some science applications of exponential functions. Again, if you need help with using whatever calculator you're using or whatever program you're using, it is important to get the exact answers before using the calculator. And if you need any more help, you can always come in and ask questions during class or come in the tutor. Until next time, stay safe.